trying to create an algorithm that would tell for us, given a certain context-free grammar, call it G, is that grammar incapable of generating a string? Or in other words, rephrasing the same question, is the language of that grammar the empty string? The language of that grammar is the empty string. So we translate that problem into a language. So here's a language, call it E, CFG, subscript CFG. I'm getting hot. Let me switch on the air conditioning. And you'll see that the fact I've got my cap on, the lights on, I'm still having problems going to bed on time. When 2 or 3 a.m. rolls along, I'm really in the thick of something and don't want to stop. So I tend to crib and then I sleep in. I get I don't use an alarm clock. I just wake up when my buddy wakes me up, and that way I sort of run out of daylight. By the time I've written the board, which seems to take me about 3 hours, I've done it so many times, it's about 3 hours. And then it's about 2 hours filming. So, you can do the math. So things start to get a bit darker, 5:30, it's late October now. So I need to start around noon. I need to start writing the board around noon, just do the math. And if I'm waking up after that, I run out of daylight. Okay. Alright, so question is, given a grammar, any grammar, context-free grammar, G, find an algorithm that can determine whether the language generated by that grammar is, the empty set. In other words, that it just doesn't generate any strings at all. Okay, same thing. Alright, so create a language where all its members are of this form. Now the Anglo brackets, of course, so that means you've encoded or represented the information of your grammar in string format, so that it can be input into a Turing machine. Okay? And finding an algorithm that can answer this question, is this grammar G? Is it a grammar whose language is the empty string? That's the question. That's the computational question. Okay, and you translate that into a language type question, membership of a language type question. Yes or no? Is this string? Is it a member of this language or not? If it is a member of this language, well, the condition that this string is in this language, is that it satisfies this property, and that is that the language generated by the grammar G, whatever it is, CFG, it has to be a context-free grammar, is the empty string. In other words, this grammar generates 0 strings. Doesn't generate any. Right? Okay, so if we can find a Turing machine, in other words an algorithm, same thing, that decides this language, what does that mean again? It means if a Turing machine decides a language, it means that Turing machine accepts for every string in the language, and it rejects any other string. Any other string. So if you're talking about all strings. So that tiny subset that is accepted, the Turing machine would accept all members of that language, or all members of this, and all the other strings rejects. But it's either one or the other, right? So the Turing machine is a decider, and therefore this language is decidable. And by definition that means that there is a Turing machine that decides the language. By definition that means it accepts every string in the language, right? And it rejects all other strings. Okay. There's no looping, right? The Turing machine decides. You know, it takes a string and uses the grammar, okay, and it accepts or rejects. In other words, it decides whether this G generates no strings or the opposite. So it generates at least one string. Okay. All right. So proof idea. So we have two and a bit squares on the proof idea, let alone the proof. So fairly involved. Yeah, we're getting more and more complex. All right. So theorem 4.8, and this language E, CFG, E for empty, right? Let's talk about the empty string. Be careful. The empty set, right? Different things. Subtle difference. But this is a set with nothing in it. Philosophical questions abound. All right. Okay. Okay. So how to go about doing this? Well, one idea is we might take the Turing machine S from the previous theorem 4.7, and maybe we need to do a bit of reminder. Because theorem numbers don't mean much, and Turing machine letters, you know, labeling them with letters, that doesn't mean much either, right? So we have to go back and remind ourselves. So what? So theorem 47. What was that about? So I'll just check. Yeah, this just to refresh on. So the language A, CFG, is a decidable language. And what is that language A suffix CFG? Well, it's the set of strings, and each string is a ordered pair, G, W, and so G is a grammar and W is a string, and that ordered pair, G, W, is a member of the language if that grammar can generate the string W. Okay, so in other words, you're translating that from going backwards, going from a language problem back into the original computational problem. So that means effectively that your Turing machine S can make a decision whether a given grammar G can generate the string W, whatever it is, whatever the grammar is and whatever the string is. Okay, so S decides whether G can generate little w, the string. Okay, sufficient refreshing. Okay, so that's one idea. We'll just use this Turing machine S and just have a look at all what do we do? So it just looks at, effectively it looks at all strings. Although it sounds a bit crazy because it'll just be an infinite number. Let's just check it. We can test whether CFG generates some string. Okay, we've just done that. Now, how would you determine whether the language? Now, remember, a language is a set of strings. In this case, the language generated by this grammar, it's just the set of all strings that the grammar generates. Okay. And the computational question is L of G, the language generated by the grammar, is it the empty set? In other words, no strings. So this G generates no strings. That's the computational question. Well, here's one suggestion, and it's sort of so silly, dumb. You may laugh at it, but it's just a lead into a smarter way of doing things. All right. So one bad idea, if you like, is you just look at all possible strings, okay, one by one, and see if the grammar can generate it. So you're given the grammar, right? That's here. Well, for all possible grammars. So one at a time. You're looking at a grammar. I've got to be careful here. We're talking about a particular grammar or any grammar? I think any is up, not a particular up. So it's just any context-free grammar. So you're talking about what? For all, you're testing for all grammars and then for all strings, and seeing whether the particular grammar G you're working on at the moment, which is just one of an infinite number, could generate a particular string. So there's an infinite number of grammars and an infinite number of strings. Sounds nuts. Okay, so but there's an infinite number of strings to try. There's no mention about an infinite number of grammars. Bit of a question mark about that. Okay. Anyway, so this method would run forever. So obviously impractical, right? So forget about that approach. All right. So we need a different approach. So how to determine whether the language of a grammar is empty? Because that's what you need, right? So if you have an algorithm, because that's what we're trying to find. We're trying to find an algorithm, or a Turing machine, same thing, which answers a question for a given grammar, a context-free grammar, and a given string. So here, oh wait a minute, there's no string. So for a given grammar, does it generate 0 strings? That's the question. That's the computational question. Right? Is the language generated by this grammar the empty string? In other words, it generates no strings. Okay. So now you can translate. So focus on that question. Will the grammar generate no strings? Okay. That's sort of like the key idea now, and typically any sizable proof will have usually some central idea that's the heart of the proof. I keep saying that, but it's a valuable lesson. So the core of this proof now is to concentrate on how could you show that for a given grammar that it does not generate any strings. Okay, that's the core idea. All right, run with that. Well, how would you show that for a given grammar there are no